Hey everybody, today we're going to talk about model selection. So there's a basic principle when it comes to model selection. Principle. It's the following. It's Occam's razor. Occam's razor, which is a philosophical principle that says all other things being equal, simpler explanations are better. The idea is, all other things being equal, simpler explanations are better than more complex ones. In our case, we're not going to be so much talking about explanations, but rather models. So the act of model selection, when selecting which model is best, you need to balance goodness of fit versus complexity. Meaning, how well does model fit the points? How well does model fit points versus how complex? All right. So, recall from earlier we saw in our lecture notes, so let me go to the course webpage here. Okay, we saw this two models for, where was it? Down here in lecture 7. We had two models for interspecies competition. The left one, which is simple because it treats all competitors the same, and the right one, which is more complex because it treats all competitors differently. Let's delve into the specifics of model selection. In the link that I've shared to Modern Dive, chapter 6.3.1, we have two example models. So the data points on the left are the same as the data points on the right, and this is figure 6.7. It models the relationship of instructor age and the teaching score they received, along with gender, which at the time of the study was recorded as a binary variable. So these are actual teaching scores given to instructors at the University of Texas, Austin. And we see here that we have two competing models, the interaction model and the parallel slopes model. The interaction model allows for different intercepts and different slopes, whereas the parallel slopes model says, okay, they can have different intercepts, but are required to have the same slope. And we see here that in all cases, as instructors age, at the University of Texas, Austin, they tended to receive lower teaching scores. But in an unfortunate case, look what happens to the female instructors, again, assuming a binary variable, because that's how it was recorded at the time, that in fact, the slope for age is actually more negative. So this is suggesting that as female instructors age, they pay a bigger penalty in teaching score than the male instructors do. So when you present these two models to students, they often say, wait a minute, why would you pick this model on the left or on the right when clearly if you have an interaction model with separate slopes and separate intercepts, they form an X over here. Why wouldn't you take this model versus that model? But again, remember our idea of balancing fit versus complexity. You only want to use the more complex model if it is warranted to do so. So let's go back to our notes here. Use more complex model if complexity is warranted. Meaning, If you don't need that complexity, then don't use it. Let's go back and look at another example. Now let's look in figure 6.8. The data points on the left and on the right are the same, and it is exposing an unfortunate trend in Massachusetts high schools. That as the proportion of students in a particular high school come from an economically disadvantaged background, there is an associated drop in math SAT score. This leads individuals to wonder, what is it that SAT scores are actually measuring? But once again, we have an interaction model here where you have 3 lines with 3 intercepts and 3 slopes. And on the right, we have the parallel slopes model where you only have 1 common slope but 3 intercepts. Over here, if you look at the quality of the fit of the lines, they don't look all that different. Meaning, these points aren't going to fit these 3 lines any better than over here. So in this case, you would favor the simpler model. The idea being that the additional complexity of the interaction model here is not warranted. But again, that is my opinion. I don't think it's warranted. Let's look at some R code. We're going to load those exact same data points here. And then we're going to fit, those are in MA schools. Then we're going to fit both regression models. All right, so remember, the way you fit a parallel slopes model is you do plus school size, which is categorical, and then the interaction model has times school size. So if you go back over here, school size is the categorical variable that splits up the schools depending on size. Let's look at the regression tables for both these regression models using the tidy function from the Broom package. This is kind of like the summary function, but it returns a tidy data frame. Okay, great. We have the intercept for the baseline group of the small schools. We have the 2 different intercepts for the medium schools and the large schools. And finally, we have the common slope for percent disadvantage. That is the parallel slopes model, which assumes a common slope. But now, here is the regression table for the interaction model. We have the slope for the baseline group of size small. We have the offset or difference for the medium-sized schools, the offset for or an intercept for the large school. We have the slope for percent disadvantaged for the small schools, the difference in slope for the medium schools, and the difference in slope for the large schools. Now, unfortunately, these offsets and differences in slopes can get a little bit confusing. But the key thing to note here, though, is in the simpler model, there are k equals 4 parameters to estimate. This one, this one, this one, and this one. For the more complex interaction model, we have 6 parameters to estimate. This one, this one, this one, this one, this one, and this one, corresponding to the 3 intercepts and 3 slopes. So let's go back to our notes. So what was the, let me get the figures number of that. For data in Modern Dive figure 6.8, the simpler parallel slopes model has k equals 4 parameters. The more complex interaction model has k equals 6 parameters. Using the eyeball test, Bert prefers the simpler model. Again, in this case here, because the way the lines play out aren't all that different, why not go with the simpler model? But now, let's do this a little bit more rigorously and numerically. So here are some numerical measures for model selection. First, recall r squared. R squared is a value between 0 and 1, where, recall this from regression, that for a given regression, r squared is 0 if points do not fit line, I should say regression line, at all. Whereas you have an r squared of 1 if regression line fits points perfectly. Okay, so remember that value called r squared. But here is the first numerical measure. It is r squared adjusted. R squared adjusted looks something like this. It is 1 minus n minus 1 on the numerator, n minus k plus 1 on the denominator, times 1 minus r squared. Where n equals number of points, k equals number of parameters, and r squared is just r squared. So this balances, r squared balances fit as represented by r squared, because remember, r squared is a measure of fit, versus complexity as measured by k, the number of parameters in your regression. So it balances the two. So let's look at two examples. Example, as r squared goes up, all right, what happens as r squared goes up? Minus 1 minus r squared goes down, becoming more and more negative. But then you see up here, we have the negative sign here, right? So negative blah, blah, blah times 1 minus r squared goes up. So as fit gets better, r squared adjusted goes up. But remember, that is the fit part. So as the fit gets better, r squared adjusted goes down. But here's the opposite. As k goes up, as the complexity goes up, as k goes up, the denominator, n minus k plus 1 goes down. So if the denominator goes down, all right, what do you have? You have the term, the entire term, blah, 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 times 1 minus r squared goes up. But then if that term, blah, 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 times 1 minus r squared goes up, then minus blah, blah, blah. I should say 1 minus blah, blah, blah. 1 minus r squared goes down. That's the key lesson. As complexity of model goes up, r squared adjusted goes down. And here's the moral. Models with smaller, larger. Models with larger r squared adjusted are to be preferred. Let's go back to our R code. So check it out. Using the glance function from the broom package, we can get both r squared adjusted and r, here, let me clean the screen up and run it again. Okay, let's focus on these four numbers. This one, this one, this one, and this one. We see that both models have similar r squared. But you see here that because k is smaller for the parallel slopes model, r squared adjusted is bigger. Down here, because k is larger, meaning it's a more complex model, r squared adjusted is lower. Let's go back to the notes. So what did I call this? I called this for data in figure 6.8. For data in modern dive figure 6.8. Because, let's say, interaction model has k equals 6 versus parallel slopes model k equals 4, all right? We see that what goes on is that because the parallel slopes model, or I should say the interaction model, is more complex, because this is more complex, it has a lower r squared adjusted score of 0.694 versus 0.696. So folks, that is your introduction to your first numerical measure of model of a numerical measure of for model selection. So that was number 1. Let's take a look at another one now, number 2. Number 2 is called the, and I have to look it up because I never remembered, it is called the Akaike information criteria. This is another, or AIC is another numerical measure for model selection, where models with, models that have, I always have to remember this, models that have smaller, how do I close this? Models with smaller AIC are to be preferred. And here's the formula for AIC. AIC equals 2k minus 2 times the log likelihood. And recall, we saw that in an earlier lecture. We're not going to get into the specifics of how to compute the log likelihood in this class. This is something that you cover in math. I forget the course number, but math statistics. But here's the key thing to note. This is right here, the balance between fit and complexity. Complexity as measured by K and fit as measured by log likelihood. Let's break it down. A, all other things being equal, all other things being equal. As models get more complex, i.e. have larger K. As there are more parameters you need to estimate or more values you need to keep track of. As models get more complex and have larger K, AIC goes up. And remember, folks, we want to pick models that have lower AIC. But B, again, all other things being equal, as models fit the points better, the log likelihood goes up. And if the log likelihood goes up, then -2 times the log likelihood goes down. And remember, folks, and if the log likelihood, if -2 times the log likelihood goes down, then AIC goes down. So as the models have a better fit, you're more likely to choose it because it has a smaller AIC. Let's go back one last time to R. All right. Using the glance function from the Broom package, we also get values of AIC. So look at our two values of AIC. We have 3280, 3283. Using this criteria for model selection, it's saying that, hey, you know what? The best balance of model complexity and model fit between these two is the parallel slopes model. So again, looking at code. Because parallel slopes model has lower AIC, what is it? It's 3280 versus 3283. You are led to select this model over the parallel slopes model. Oh, sorry, over the more complex, interaction model. So again, folks, in this case here, let's go back to the image. Using this particular information, this particular criteria called AIC, it's saying that the best balance between model complexity and model fit, in this case, is the parallel slopes model. Great, thank you.